Okay, class, we're going to actually skip section 3.5. We're going to go right to section 3.7 today. So I will not have section 3.5 in the homework. We're going to start section 3.7 here. So today we're going to talk about arguments and truth tables. So we're going to make this actual practical, and we'll look at some actual logical arguments. First, define what an argument. An argument consists of two parts. One, the given statements, which we call in mathematics or logic the premises, or sometimes we call them the axioms. We don't use that in this class, but that's another term. And then we have the conclusion. So basically, the way an argument is laid out is you give me your evidence or your premises, and then you try to deduce whether or not the conclusion follows logically from the premises. Now, you might guess that the way we're going to actually determine if an argument is valid is by looking at the truth table. Okay, looking at the truth table. Okay, so how do we determine whether an argument that is given is valid? Well, this is how we're going to define a valid argument in this class. An argument valid if the conclusion is true whenever the premises are assumed to be true. An argument that is not valid is said to be an invalid argument, also called a fallacy. Okay, so as long as the premises are true, then we would say that when the premises are true, that means that the conclusion is true, then that means it's a valid argument. Otherwise, it's an invalid argument. Okay? So let's take an example of this and we'll kind of map it out. Now, before we get into actually doing this example fully, I want to at least throw this up from the book, which says, how do we test the validity of an argument with a truth table? So first of all, this is a process we're going to use. We're going to use a letter to represent each simple statement in the argument. So we're going to have a P statement and a Q statement. We're going to express the premises and the conclusion symbolically. So there's going to be some wording in the problem that allows us to express these. We're going to write a symbolic conditional statement of the form blank plus blank. So basically, what this means, guys, is that if premise 1 is true and premise 2 is true and however many premises we have, then then the conclusion is true. This is an if-then big statement in parentheses, right? This is my if this whole statement, then the conclusion, because it's got an arrow there, all right? So basically, an argument says, if this is true, and this is true, and this is true, then my conclusion is this is true. Okay, so that's how we form an argument in actual, like a court of law or English paper we're writing, where we have a thesis and a conclusion. We have our supporting premises that we're using to prove our argument true, and we're sequencing them as ands. If this is true, and this is true, and this is true, then this is true. So we're gonna form the premises from the wording of the problem. You'll see some examples here in a minute. Then we'll construct a truth table for the conditional statement in step 3. And if the final column of the truth table has all truths, the conditional statement is a tautology and the argument is valid. If the final column does not have all truths, the conditional statement is not a tautology and the argument is invalid. So we're looking basically for this thing to be a tautology, which we talked about in the last section. Okay, so now that I've kind of explained that, we're gonna go through this here. Okay, here's an argument given by Henry Brommel in I Know Your Heart, Marco Polo. It's from an article from the New Yorker. It's in your book. I got this example from the book. And we're going to kind of use, this is written in sentence form in English, and we're going to try to write it in terms of premises and conclusion. So let's read it. I can't have anything more to do with the operation. If I did, I'd have to lie to the ambassador. I can't do that. Okay, so first of all, the conclusion is asserted at the very beginning, isn't it? I can't have anything more to do with the operation. Okay? So that's my conclusion. How is he reasoning that his conclusion is true in this argument? Well, he's saying, if I did have anything to do with the operation, then I'd have to lie to the ambassador. So that's one statement. I should probably put that in blue so it's a different. So that's one of the premises. And then the next premises is, I can't do that. Okay, so your premises, I'm going to lay out this way. P is if I did have anything more to do with the operation, okay, then I'd have to lie to the ambassador. I'm not going to finish that statement just to save time. My other axiom is I can't do that, meaning I can't lie, correct? So my other axiom is I can't lie. Okay. And so, actually, you know what? I'm going to do this differently. I just changed my mind. Sorry, I wasted about a minute and a half there. I'm going to do this a little differently. So what I'm going to do is I'm going to first say there's two major statements in here, right? And we're going to break it down a little simpler. Let me change this. So P, I can do it the way I was doing it, but I'm going to do it a little bit different. I don't want to re-record this whole video, so I'm going to do it this way. So let's start with P. P being, there's two things happening in here. One, I can't have anything to do with the operation, whatever this operation they're talking about is. And then Q is, I'd have to lie. Okay? So if that's the case, if these are my two individual statements, okay, they're not compound statements, they're just simple statements, then the premises, going up here for a minute, the things he's using to justify his argument is in the blue first. If I did, I'd have to lie to the ambassador. So basically, if I did means if I did have anything to do with the operation, so that would be P, then, arrow, I'd have to lie to the ambassador, which is Q. So that's one of the premises. P implies Q. If I did, then I'd have to lie to the ambassador. Okay? So having something to do with the operation is P. And then his other premises is I'd have to lie. Well, that's I can't do that. So what would that be? Well, that if you can't lie, well, I'd have to lie. The opposite of I can't lie, I'd have to lie, is I can't lie. So that would be not Q as the other premise, because he's saying here this other premise here in the squiggly black is I can't do that, referring to the lying. I'd have to lie to the ambassador. I can't lie to the ambassador. And Q is I'd have to lie, so this is the opposite of that. So that's my two premises, and my conclusion is that I can't have anything to do with the operation, which is which is P, correct? The conclusion is P. I just realized I made a mistake up above because my premise, this premise right here, I just made a mistake, didn't catch it. This premise right here is the blue premise right down here that's underlined in the statement, okay? It says, if I did have anything to do, well, that's a little confusing because the P is I can't have anything to do, so the if I did have anything to do is the opposite of not being able to have anything to do with the operation. So this is actually a not P. That's the only difference. So it's not P implies Q is premise 1, not Q is premise 2, and conclusion is P. All right, so now what we do with those is we form our argument. So I'm going to erase some of this. So now that we have our premises and our conclusion represented symbolic, we don't need the statements anymore. So what we do is we create an argument. And the way we create the argument is by doing what's written here. We take premise 1, put in parentheses, not P implies Q, and not Q implies the conclusion, which is P, the way we wrote it. So what I need to do is make a truth table for this, just like we did in the previous section, where I do a P and a Q. Looks like I'm going to need a not P column and a not Q column because those both show up. It's kind of a hard example, but we'll get it. And then I need a not, looks like I need a not P implies Q column for this one. Then I need the not P implies Q and not Q. And then I need the final statement, which I'm not going to write, but the final statement is this whole thing right here. Okay? So let's start off, P and Q. So we do our true, 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 false, false, true, false, false are all my possibilities. Not P is just the opposite of the P's, so that'd be false, false, true, true. The not Q's would be false, true, false, true. Okay, not P implies Q, so we're looking at this not P and we're going that direction with each of these. For the not P implies Q. So the only one that's going to be false is this true false one, if you remember how the arrow conditional statements work for the truth table. So this one is false. Okay, and all the rest of these look like they're true because true followed by true is true, false followed by false is false, false followed by true is true. So these are all true, and that's the only one false. The only one that's false in the conditional truth table is the one where we start with true and then we arrow over to false. We're going backwards in the table because of the way they appeared in the order. Okay, now I'm comparing in red with this not P implies Q and not Q. I'm comparing these two columns, and it's an and. So we got to look at our and truth table. Well, the only time it's going to be true is when they're both true, which would be right here. The other examples are all false. Okay, now I'm going to take in blue this column and arrow it all the way over to the P column. So first I'm going to get false. So first I'm going to get false true, which false arrow true, if you go back to your truth tables for the, false, again we're doing an arrow here for this case. False arrow true is true. True arrow true is true. False arrow false is also true if you go back to the conditional truth table. And false arrow false is true. So this argument is valid because it's a tautology. They're all trues. So the answer is this is a valid argument in this case. That's a hard problem. There was a lot there. We're going to do some other ones to try to get you more acquainted with this. So don't freak out too much right now. This is a very confusing topic. I'm anticipating that tomorrow, especially on these truth tables, we're going to spend a lot of time in the Zoom meeting on these because they are not easy. Okay, let's do some examples, backtrack a little bit, and that was kind of a hard example just to introduce kind of where we're going, but we're going to build up to it a little bit now, starting with some simpler ones. So let's say I give you that my premises, so this is how it's going to be written in the book, where I give you a premises like not P implies Q, similar to what we just did, and then I'm going to give you another premises, which would just be P, and then I'm going to say therefore, this means therefore. Okay, that means therefore, that little three-circle thing, triangle. Therefore, P. Okay, so the way we draw up the truth table for a logical statement for this is we take premise 1 and premise 2 and put an and between them. So we'd go not P implies Q and P. And then that's going to imply, so these are my premises which will imply the conclusion, or if If the premises are true, then the conclusion, okay? Then that's P. So the question is this a tautology? Which would mean it's a valid argument. Okay, that's the question I'm asking. Is this a tautology? Okay, so, and where I'm getting this from, whoops, didn't mean to do that. Where I'm getting this from is from this step right here. We take our premises, we separate them by an and then we put an arrow toward the conclusion. That gives us our logic statement. Okay? So, let's draw a truth table for this. Okay, I've got it right there. So we have to build the truth table like we've done in the previous examples. So I've got my P and my Q. Okay, I've got true, 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 false, false, true, false, false. That's our standard pattern. We're going to have a not P column because there's a not P that appears. We're going to do the not, we're going to build this now. We're going to have that column. Then we're going to have the not P implies Q and P. That's the next one. And then we're going to end with the final. Okay, so let's do this. So not P would be the opposites of P. So that'd be false, false, true, true. Not P, arrow Q. So I'm basically in red. I'm arrowing from this F to that. Oh, sorry. Yeah, not, I went too far. My bad. I'm arrowing from the not P to the Q. So that'd be right here. F arrow T, if you go back to your table, is true. F arrow F is true. T arrow T is true. And T arrow F is false. That's the one time with the arrow that we're false, when we have T arrowing to F. Okay, so now we do this column, and the P column together. So now we're going to go from here to there. And it's an and, right? Well, it's not an arrow. I should underline that. We're going to do this and this. True and true, because we're using and, right? True and true is true. True and true is true. True and false is false. False and false is false. Okay, now we're doing an arrow. And that arrow is going from this column, this last column that we just did, arrowing all the way to P. So we're going to arrow all the way to P. True arrow to true is true. True arrow to true is true. False arrow to false is true in the conditional truth table, and false arrow to false is true. So this is a tautology. So the answer is yes. This is valid. Argument would be my answer. Okay, so really this is just a lot of truth table work, except for we've got to form our initial logic statement here. Okay, let's do some more of these. Okay, at this point I'm going to put the Easter egg in, which is the 6-digit number. Here it comes. It's 168999. 168999. You want to jot that down. Okay, so we're going to do an example here. Okay, and this one it's in words. It's like the one we did before, only that one was actually harder than this one. So we're going to do this one. We're going to first have to break this down into some simple statements, okay? So we're going to do that first. So if a metro rail system is not in operation, there are traffic delays. Over the past year, there have been no traffic delays. Over the past year, a metro rail system has been in operation. Okay, let's break this down into simple statements. So first of all, there's a couple simple statements in here. One is the metro rail is in operation. Okay, that's a simple statement. That's one of the simple statements in here. And the other one is there are traffic delays. So we're basically looking at two big ideas here. The fact that there are we're looking at whether the metro rail is operating and whether or not there are traffic delays. Now we're going to form our two statements, okay? Our premises here are in red. Okay, so if I go over here in red and express my premises, if a metro rail system is not in operation, okay, that is not P, then, there's no then written there, but since it's an if at the beginning, we know it's an if then, even though the then is not needed in English, then there are traffic delays. That'd be not P implies Q. Okay, so that's premise number one. Premise number two, over the past year there have been no traffic delays. Okay, so that'd be not Q, correct? That would be not Q. So those are my premises, 1 and 2. My conclusion, therefore, over the past year, a metro rail system has been in operation. So that would be P. Therefore, P. Okay? Which is, the last statement is basically the metro rail is in operation. That is P. Okay? So my actual full statement would be, I take premise 1, put an and do premise 2, and then that should imply my conclusion, right? That's my formula. So we have two premises. So this would be not P implies Q and not Q. That whole thing should, and I should probably put brackets around that, make it cleaner. That whole thing should imply P, which is my conclusion. So now I just need to erase a little of this because I don't need this anymore. I need to make my truth table now. So I get my P and my Q here. And I build this thing. So I'm going to need a not P, and I'm going to need a not Q. And then I build and do the inside here. I need a not P implies Q. Then I need a not P implies Q and not Q. And then I need my final, which is my if then statement right here. Okay? So P, we do our standard. It's true, 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 false, false, true, false, false. Not P would be false, false, true, true. Not Q would be false, true, false, true. Not P implies Q. Okay, so with that, I'm using these two here. False, arrow, true. Remember, we're going from, the arrows are going this way because we're starting with not P. So false, arrow, true is true. False, arrow, true again is true. True, arrow, false is false. And true, arrow, false. You know what? I did that wrong. Dang it. Getting the column. My bad. So, my bad. I did the wrong columns. So, rewind. We're actually doing these columns. It's not P implies Q. I was thinking it was not P. So, not P implies Q is from here to there. False, arrow, true is true. False, arrow, false is true. True, arrow, true is true. And true, arrow, false is false. That's the one false. Remember that? Okay, now I'm going to do this column ANDed with the not Q column. Remember, the only time it's true is when they're both true, which would be right there. So this one's false, this one's false, and this one's false because there's a false in each one. Remember, we're doing the AND. So for AND, they both have to be true. And then my final is I'm taking this column, right, and I'm arrowing all the way over to P. False, arrow, true is true. True, arrow, true is true. False, arrow, false is true. And false, arrow, false is true. So this is valid again. This is a tautology since they're all trues. So this is valid. This is my final answer. So notice what I did is there's an if-then statement here, and then there's just a single statement and a single statement here. I broke this down into individual single non-compound statements, and then I built the logical statement on the basis of that using the premises added up, which I have here. We do premise 1 and premise 2. If there were 3 of them, we do 1 and 2 and 3. And then we develop our full logic statement. We create a truth table, and we're looking to see if it's all true or if not, or if it's not. Okay, I think that should get you started on these problems. They're not going to be easy, but I think you can start handling them. And then I'm going to go through some more tomorrow in class, in the Zoom meeting, and I anticipate you're going to have a decent amount of questions on at least this for sure, this section, the last one. So don't fret if you're a bit confused. We'll get it sorted out tomorrow.